As another example of using this ijk notation, in fact I wrote this up here, let's actually put a k in here. Keep saying k. There we go. As another example of using this ijk notation, I wanted to point out that expressions like instantaneous velocity is equal to the time derivative of the position vector also work perfectly fine using the ijk notation. In this case, you would take the time derivative of each term, just like you would any other time, and the vector itself is treated like a constant. You know, if I took the time derivative of this term, for example, the 3 would just go along for the ride. Well, so would the I. Neither of them changes with respect to t, and so I would just end up with a time derivative of each term, and the same way I would if I didn't have i's and j's and k's. Notice this middle term here, I say term, this is actually two terms, both being multiplied by the j hat. In the same way that a generic expression for position in one dimension could have multiple terms, like 2t minus 3, or t squared plus 8, or whatever else. That's true individually of every separate component. And so in this case, we have an entire expression, 2t minus 3, that represents the vector's component in the j direction, but that's perfectly fine. If I wanted to figure out the instantaneous velocities expression from this, I would just take the time derivative of this vector, where I would say, all right, 3 just goes right through, it's being multiplied by a constant. The I hat also just comes right on down, and the time derivative of t squared is 2 times t. So I get 3 times 2 times t to the first times I hat. So in other words, I would get 6t I hat. If there were no I hat here, the time derivative of this term would have been 6t. So you can see it's just simply the I hat goes along for the ride. Over here on this term, the j hat will just come along for the ride, and we will take the derivative of every term just like we would normally taking the derivative of a polynomial. The derivative of 2 times t is simply 2, since the derivative of t to the first is t to the 0, which is 1. And then the derivative of a constant is 0. So this term just ends up being 2 times j. If I'd taken the time derivative of 2t minus 3, I would have simply gotten 2. When that's multiplied by j, I simply get 2j. And then likewise, you can see where this is going. The 5 comes down here. The time derivative of t cubed is 3t squared. Multiply by the power, subtract 1 from the power. And then k hat comes down for the ride. And so while without the k hat, the derivative of 5t cubed would be 15t squared. With the k hat, it's simply 15t squared k hat. And if I wanted to know the instantaneous velocity at a particular instant in time, I would just plug in the time, and I would get a velocity vector with x, y, and z components. So I would get some specific velocity vector for any point in time. If I wanted to know the one single component of the velocity vector at any point in time, I could do that too. The x component of the velocity vector at any point in time is given by 6t. The y component of the velocity vector is just this constant 2. No matter what's happening with time, the y component, the j hat component of the velocity vector is simply this constant 2. And this other expression could give me the magnitude of the z component of the vector, if I needed to know that. Or if I wanted to instead calculate the acceleration at any given point, I could just take another time derivative. At this point, this entire thing is a constant. It's just a number times my constant unit vector. And so I would get 0 for the entire time derivative of that one. So I'm not going to bother to write the 0. And the time derivative of that last term is 30t k hat. And so you can see this works exactly the same way as it did if there weren't I, j, and k's. It's just essentially what you're doing is the x component of velocity is equal to dx dt. That's right here. And the y component of velocity is equal to dy dt. That's right here. And ditto, this is dz dt. You're just doing it all together in one big long equation, which a lot of times can save you a lot of time. That was, sentence got away from me. Oh well. That's the point.